Hello everyone, I'm Yao Li from Chang'an University. In this lecture, we are going to learn the part 2 of conventional triaxial test. Now, let's have a look at the CU test. In the step 1, its drainage is open, so there is no excess pore water pressure. As a result, its effective stresses equal total stresses. In the step 2, its drainage is closed after dilatoric stress is applied. Excess pore water pressure is generated. Total stress equals effective stresses plus excess pore water pressure. Sigma 1 equals consolidation vertical stress plus dilatoric stress minus excess pore water pressure. Sigma 3 equals cell pressure minus excess pore water pressure. At failure, total and effective sigma 1 and sigma 3 can be calculated in the same way. Those figures show typical results of a CU test for dense sand or over-consolidated clay with increasing axial strain, which is caused by the continuous movement of the load rod. Dilatoric stress increases first and then decreases till a constant value is reached. Its excess pore water pressure increases first and then decreases. For loose sand or normally consolidated clay, with the increasing axial strain, dilatoric stress continuously increases. Its excess pore water pressure continuously increases. Those figures present results from two individual CD triaxial tests with different cell pressures, indicated by sigma 3a and sigma 3b. In the top left figure, it can be seen that under different cell pressures, the peak dilatoric stresses are different. In the bottom figure, two more circles are drawn using the two sets of data, mainly the sigma 1 and sigma 3 at failure. The more Coulomb failure envelope can be drawn. Friction angle phi and cohesion C can be determined. It should be noted, since there is excess pore water pressure in CU triaxial tests, effective stress and total stress given different more Coulomb failure envelopes. As a result, different friction angle phi and cohesion C can be determined. In CU triaxial test on normally consolidated clay, the effective friction angle is greater than friction angle determined using total stresses. And effective cohesion and cohesion determined using total stresses are both zero, as shown in that figure. The unjoined shear strength SU is dependent on the level of effective stress under which the soil has been consolidated. It increases as the consolidation stress increases. The relationship between consolidation stress and unjoined strength for normally consolidated clay is linear. In CU triaxial tests on over-consolidated clay, the effective friction angle is greater than friction angle determined using total stresses, and effective cohesion is smaller than the cohesion determined using total stresses, as shown in the figure. It should be noted that in over-consolidated clay, negative pore pressure develops at failure. In normally consolidated clay, positive pore pressure develops at failure. This figure shows total stress failure envelope obtained from CU test in over-consolidated clay. It can be seen that the more Coulomb failure envelope is no longer a straight line when the over-consolidated clay changes to the normally consolidated clay under certain vertical stress. Generally, in a CU triaxial test, cell pressure is applied while drainage valve is open, and dilatoric load is applied while drainage valve is closed. Excess pore water pressure is developed during loading. Sample must be fully saturated so that the effective stresses can be calculated. Effective cohesion and effective friction angle can be measured from effective stress Morse circle. In unjoined triaxial test, there is no volume change during shear, and pore water pressure develops instead. Unjoined shear strength can be measured from total stress Morse circle. CU triaxial test can be used in the evaluation of stability problems where soil is fully consolidated, and then additional stresses are quickly applied. Now let's have a look at the UU test. In the step 1, after sampling, no stress is applied on the specimen. In the step 2, its drainage is closed, cell pressure is applied, excess pore water pressure is generated. The sigma 3 equals effective sigma 3 plus excess pore water pressure. It should be noted that the applied cell pressure has a relation with the excess pore water pressure. The change of excess pore water pressure equals B multiplied the change of sigma 3. B is the Skeleton's pore water pressure parameter. It is used to check if the specimen is saturated. For saturated soils, B equals 1. For dry soils, B equals 0. For partially saturated soil, B is greater than 0 and smaller than 1. So, for saturated soils, the applied soil pressure equals excess pore water pressure in the step 2. In the step 3, axial load is applied where the load rod, and the drainage is still closed. Additional excess pore water pressure noted by delta U D is generated. Here, a new parameter A is introduced. The change of excess pore water pressure equals A multiplied B multiplied the change of diatoric stress. The effective stress can be calculated accordingly. This figure shows a monochrome failure envelope for saturated clay under total stress condition. All tested specimens have the same shear strength since no consolidation is allowed. Therefore, on-joint friction angle for saturated clay is 0. UU triaxial test can be used to evaluate the short-term stability in normally and over-consolidated clays. Compared with direct shear test, triaxial can control the drainage condition and measure the excess pore water pressure, so there is more options of testing condition. However, triaxial takes longer time in sample preparation, loading, saturation, and balancing the excess pore water pressure. On the contrary, direct shear test is simple and fast in determining friction angles. This figure shows the application of soil tests for slope problem. Triaxial compression test, direct shear test, and triaxial extension test can be used to simulate the soil behavior at different locations. It should be noted that in the lecture, all triaxial tests are triaxial compression tests, which is mostly used compared with triaxial extension tests. Considering the construction of footing, we may use different triaxial tests under different conditions, mainly the consolidation condition and the drainage condition. If the construction was slow and the pore water pressure was allowed to dissipate, there would be consolidation and drainage condition. Accordingly, the CD test results can be applied. If the construction of the footing was rapid and the pore water pressure was not allowed to dissipate, there would be no consolidation or drainage. Accordingly, the UU test result can be applied. If the construction of footing was forced to stop due to some unexpected factors, to catch up the schedule, the construction needs to be accelerated. There would be consolidation but no drainage. Accordingly, the CU test result can be applied. Here are all the contents in this lecture. Thanks for your listening and see you next time.